So we are on section 5.4, which deals with exponential functions. And so we're going to kind of review over like what an exponential e to the x function looks like, how to derive it, how to integrate it. Based on last section, does the natural log of x have an inverse? If so, explain why, find the inverse, and verify algebraically. So here's the deal. A function has an inverse if it's monotonic. Monotonic means it's either always increasing or always decreasing. So to tell if a function is always increasing or always decreasing, we can look at the derivative if we don't know what the function looks like. But we know that the natural log of x from a prior section is always increasing. Okay, it has an asymptote at x equals 0, goes to the point 1, 0. It's a horrible graph, but it's always increasing. So yes, the natural log of x has an inverse because it's monotonic, meaning it's always increasing or always decreasing. In this case, it's always increasing. To find the inverse, what you do is you switch the x's and y's and solve for y. So when I do that, I get x equals the natural log of y. So I take, to evaluate this and to solve for y, you take base e, you raise it to the other side, so e to the x, and you set it equal to the inside of the log, which is y. So what we just found is that e to the x is actually the inverse of the natural log of x. And you can see graphically right here, when two functions are inverses of each other, their reflection over this line, y equals x. Okay, we're going to skip the algebraic proof. Basically, the algebraic proof is if you compose one with the other, either way, you should get x out of it. All right, so what you need to know is the basic shape of e to the x. All right, it has an asymptote at y equals 0. It has a point at 0, 1. It increases from left and right. Remember, a function and its inverse, the x and y switch. So the natural log of x has the point 1, 0. So e to the x has the point 0, 1. So let's look at these translations to the graph. This x plus 1, when you set it equal to 0, you get x equals negative 1. That means it shifts to the left 1. The asymptote does not change. It's at y equals 0. The point, instead of being at 0, 1, it is now at negative 1, 1. And it still increases from left to right. This plus 1 on the end moves the whole graph up 1. So you have the line y equals x as your asymptote. Your point is usually 1 above that. It's not shifted left or right because this is just plain old x. And it increases from left to right. Just make sure you show the tick marks. You don't have to label anything, but if I can see the marks, then we're good enough. For negative e to the x, all right, the asymptote stays the same because there's nothing added to it or subtracted at the end that would shift it up and down. This negative in front is huge. That flips the graph up and down. So instead of the point being at 0, 1, it is flipped down to 0, negative 1. And it looks like this. So instead of increasing from left to right, when you flip it down, it decreases from left to right. And last but not least, this negative x actually flips it left and right. So the asymptote stays the same, the point stays the same, but instead of increasing from left to right, this decreases from left to right. Okay? So there you go with that. All right, now solving exponential equations. So what you want to do is you want to get the exponential by itself. Example 1, it's already by itself. Step 2 is you take the natural log of both sides. So you have the natural log of 7 equals the natural log of e to the x plus 1. Evaluate the right-hand side. Any exponent of a log gets moved out in front. Oh, this is freezing. Okay. Equals. So the exponent gets moved out in front. So this x plus 1 moves out in front, and that's times the natural log of e. You should know that the natural log of e equals 1. And another thing you should know is the natural log of 0, or wrong thing, thinking ahead. The natural log of 1 equals 0. Okay, so these are two that you should know that are important. So natural log of e equals 1. So now we're just solving x plus 1 equals the natural log of 7. So x equals the natural log of 7 minus 1. And you would leave it exact like that. All right. Example 2, you got to get the exponential by itself. So you subtract 8 on both sides. So you get e to the 2x minus 4 equals 2. Then you take the natural log of both sides. The left-hand side just ends up turning into the exponent 2x minus 4 because that moves in front times ln of e. ln of e equals 1. And now we can solve for x by adding 4 to both sides and then dividing everything by 2. So we get the natural log of 2 plus 4 divided by 2. You cannot reduce anything. You can't reduce into the inside of a natural log. So therefore, you can't reduce that 4 because it's attached to something else by addition. All right, moving down, we're solving logarithmic equations now. So to solve logarithmic equations, you want to get the log by itself, which it is in example 3. Then you want to exponentiate. So this is base e. So we take e, you raise it to the other side, which is 5, and you set it equal to the inside of the log. So base e raised to the right-hand side, set it equal to what you're taking the log of. And now you can solve for x by adding 3 to both sides, and then you would divide everything by 2. Okay. And example 4, we got to get the logs by itself. So what we're going to do is we're going to subtract ln of 3 from both sides. And then if you can, combine the logs. So when you have two logs that are being subtracted, you can make it one log by taking the first inside and dividing it by the second inside. Now you're going to exponentiate. So you're going to take base e and you raise it to the other side. So you raise it to the second and you set it equal to the inside of the natural log. And now you can go ahead and solve for x. So you would multiply both sides by 3. And then subtract by 3. And then divide everything by 4 to get x by itself. There you go. Okay. All right, so that is review of things that you've seen before. The new thing is taking the derivative of an exponential. It's actually really, really easy. To take the derivative of an exponential, you keep it the same, and then you multiply by the derivative power. That's what this stands for right now. So example 5, you keep it the same as the original, and then you multiply by the derivative of the exponent. Well, the derivative of the exponent here is just 5. So your answer would be 5e to the 5x for the first one. So you keep it the same times the derivative of the power. So example 6, keep it the same times the derivative of the power. What's the derivative of the power here? Derivative of the power is 3x squared. So all you do to clean it up is move that 3x squared out in front. And there you go. Okay. Next one. Leave it the same. So e to the negative 3 over x times the derivative of the power. Now you have to be careful here. So the power, when you rewrite it, is negative 3x to the negative first. Be careful deriving that. So the negative 1 comes out in front. Negative 1 times negative 3 is positive 3. X to what power? You subtract 1. So it'd be x to the negative second. So then your final answer would be, and I would move this part in front, 3 over x squared times e to the negative 3 over x. And there's your derivative. So remember, derivative of an exponential is easy. Keep it the same times the derivative of the power. So for example 8, keep it the same times the derivative of the power. Now the derivative, because of the inside here. So derivative of sine is cosine. Keep the inside the same times by the derivative of the inside. So it'd be times 3. And that's it. And then you're just going to make it look nicer. So I would move the 3 cosine 3x out in front times e to the sine 3x. Right? So that's how you differentiate an exponential function. And the last part of our lesson is to integrate. All right, so I did start something here. So remember to always watch out for product, quotient, and chain rule, which were not seen in the above example. So meaning like if you had something like this, and I said take the derivative of this. Okay, this is two separate functions. You got to start with product rule. All right, that's what I mean there. Okay, and you didn't really see that in these examples. All right, last but not least, when you integrate e to the u du, you get e to the u plus c. So here's another hint, right? When you're doing integration, if you can't integrate it normally, then you're thinking, what is my u, what is my du? That's called integration by substitution. When you're dealing with exponential functions, your best bet when it's by itself is to make u the whole power. And then du would be the derivative, which is 3 dx. So you have to put a 3 in, and if you put a 3 in, you put a 1/3 on the outside, and look what you're left with. This is going to be e to the u, and then the rest of this right here is du. Well, e to the u, du integrates to just e to the u. So this is e to the u, which I'm going to plug my u back in, 3x plus 1 plus c. And remember, you can always check your answer to an integration problem by doing what? By deriving, and you should get back what you started with. We now know how to derive an exponential. All right, example 10. So the main thing I see in here is an exponential. I'm going to try to make u the power and see if that works. My derivative would be 2x dx. I know I'm on the right track because I have an x dx in there. What I need is a 2, not the 5. So what you can do, if you don't want a constant in there, you can pull it outside. All right, I'm going to put the 2 in that I need as long as I multiply by a half on the outside. So now it's 5 halves on the outside. This e to the x squared becomes e to the u. The rest of it, the 2x dx, becomes your du. And we just learned that e to the u du integrates to e to the u. So it would be e to the x squared, because that's my u, plus c. Okay. All right. So next one here. Okay, what do you think you want to try us? Good, the exponent cosine. The derivative of cosine is negative sine. How do we know we picked the right u? Because your du is basically in there except for a number. I need a negative on the inside, so I'm going to put a negative on the outside. This ends up being e to the u, and the rest of the stuff in there is my du that I'm substituting in. And e to the u integrates to e to the u, and then plug my u back in, plus c. All right, we're going to skip 12. We're going to go to example 13. So I'm going to try to make u, what in this case? The power, so 1 over x. Now 1 over x is the same thing as saying x to the negative first. So the derivative of x to the negative first is negative 1 x to the negative second times dx, which is negative 1. Sorry, this is freezing. Negative 1 over x squared dx. All right, you know you're on the right track because look at this. You basically have a 1 over x squared dx in there. You negative on the inside, which means you put a negative on the outside, and this ends up being e to the u, and the rest of it, this isn't over du, it's just times du. Nothing should ever be over du. The 1 over dx, 1 dx over x squared, the negative 1 over dx over x squared is my du. So e to the u du integrates to e to the u. I'm going to plug my u back in, plus c. Okay? So with example 14, what are you going to make u? Tangent, derivative of tangent, secant squared. Oh, you know what? I realized there's a problem with this problem. Let's see. Make this cosine squared. Okay, that'll work nicely. So change this bottom to cosine squared. Now, this works because 1 over cosine squared, that can be rewritten as secant squared. Right? 1 over cosine squared is secant squared. And now you have everything in there. So this turns into e to the u du, which integrates to e to the u plus c. All right. Looking at, let's just do a couple more here. I know there's only 3 left, but looking at example 16. So there's a lot in here. And when you have trig in here also, and e is on the inside of trig, you're going to try to make u the inside of the trig function. Okay, so my du would be derivative of an exponential is keep it the same times the derivative of the exponent, which is 2x times dx. We just learned that up here, okay? Now, we know we're on the right track because, look, my du is basically in here. There it is, right? The x, e to the x squared is in there, but I need a 2. So I'm going to put a 2 in. If I put a 2 in, what goes on the outside? 1/2. So this ends up being 1/2 the integral of tangent of u, and the rest of it is du. Now, you have a formula sheet that I'm allowing you. The integral of tangent is negative, and then leave the 1/2, the natural log of the absolute value of cosine of u, so I'm going to plug my u back in, e to the x squared, plus c. All right, this is something where you would have a formula sheet for the integral of tangent, and I'll expect you to memorize that at this point. So the integral of tangent is negative natural log of the absolute value of cosine u plus c. Okay, sorry, I was thinking about something. Yeah, there you go. And then for example 12, we might as well just finish this. You have e's on the top and the bottom. Here's what you're going to try. Making u just 3x, not going to work. You're going to run into a problem. Because it's a fraction, multiple e's, try to make u the whole denominator. So if you make u the whole denominator, the derivative of u is 3 e to the 3x dx. And you know you're on the right track because look, you basically have it here in the numerator. You just need to put a 3 in and multiply by 1/3 on the outside. And what does this turn into? What's going to replace the top? And what's going to replace the bottom? What does that turn into? Du over u. And from previous section, du over u integrates to the natural log of the absolute value of u. plus c. Okay. And we're so close, so we might as well just finish this. So last but not least, this one right here. So you have trig in here. So if there's e's inside of trig, make u the inside of the trig. Try that. All right, if we make u e to the 2x, the derivative would be e to the 2x times 2. Because you keep it the same times the derivative power. Derivative power would be 2. All right, you know you're on the right track because look, you have the e to the 2x dx in there. I just need to put in a 2, and that means a half goes on the outside. So what are we integrating here? We're actually integrating cosecant of u, cotangent of u, and you have a formula for that. That integrates to negative, leave the 1/2, cosecant of u, I'm going to plug my u back in, plus c. All right, there you go. All right, we're done. 5.4.